Hello, this is Julio. Welcome to the first online class. In these classes we will try to advance in the course by solving the problems in the program. For this purpose, you need to do some exercises in your notebooks and send me a photo to my email in order to check that you are understanding. Let's begin. First of all, let's have a summary about the Dirac delta potential which we discussed some classes ago in order to check some of the properties. We solved the Schrodinger equation for a Hamiltonian with potential given by the expression. We had shown that there is only a bound state, which is solution to the Schrodinger equation with wave function equal to, with k being a positive constant. If we substitute this expression on the time-independent Schrodinger equation, and then use the following expressions for the derivatives of the wave function, where the sine function is defined as, one finds that the energy can only be equal to, which is the only allowed energy which satisfies the Schrodinger equation. Exercise 1. Show the expression for the second derivative of psi of x by examining the derivative of the function sine of x. Exercise 2. Check the expressions for the energy and k from the Schrodinger equation, from the expressions for the wave function and its derivative. One can check that the mean values of the position and momentum operators are equal to 0. And the mean values of the square of these operators are equal to, where the wave function psi of p is the Fourier transform of psi of x. Exercise 3. Check the expression for the mean value of the operator p square by integrating p square times the probability distribution of p. Compare this result from the one you obtained by obtaining the second derivative of psi of x from the Schrodinger equation. From the comparison, check the expression for k. By using the definition of the covariances for x and p, one can conclude that with these expressions on mind, one can now investigate the double delta potential. One can also think of a potential V of x with two deltas at positions x equal to plus minus a, that is, in this case the Schrodinger equation can be written as, the solution of this differential equation can be obtained in the different regions, region 1 for x smaller than a, region 2 for x between minus a and a, and region 3 for x larger than a. In every region, if we exclude the borders, we have to solve the free particle, which has the following solutions. The solutions in 1 and 3 satisfy that the limits for the wave function when x go to plus minus infinity are equal to 0. As the probability given by the square norm of psi of x is a continuous function at the border of these regions, then we have the same conditions for the wave functions. And by integrating the Schrodinger equation around the borders of these regions, we can obtain different conditions for the derivative of psi of x. We can obtain these conditions by using the expressions. Exercise 4. Obtain the conditions for the derivative of the wave function using these two expressions. With these, obtain the equations which n1, n3, a, and b must satisfy. From the continuity of psi of x and the discontinuity of the derivative psi prime of x, one can obtain the following transcendental expression. These equations are solved numerically by plotting the functions exponential of minus 2ka and the functions plus, minus times 1 minus k over kappa 0, and see the value where both cross each other. Exercise 5. Plot these functions for a equal to 2, kappa 0 equal to 2 and a equal to 2. Kappa 0 equal to 1 over 4, how many k's are solutions of these equations? Exercise 6. If Ka is much larger than 1, how many solutions are there? How many solutions when Ka is much smaller than 1? How many energies are there and which are their expressions? Finally, I would like to explain that as the particles which can be described by our wave function does not have a particular predilection for any specific region 1, 2 or 3, then our solutions can only have a defined symmetry, in other words they should be either symmetrical or antisymmetrical. In the symmetrical case the normalization constants must satisfy. And in the antisymmetrical case. Exercise 7. Write down the expressions for the wave functions for both symmetries and plot them. Take photos of all your answers and send them by email. julio.lopez@fistech.edu. If you have any questions or suggestions please feel free to send me a message. Good day.